Thank you for coming. My name is Jonathan Romero, and I am one of the co-founders of Zapata Computing, and I lead the professional services team, which is a team of scientists and engineers dedicated to helping our customers explore, pilot, and ultimately implement applications of quantum computing. And in the process of working with our customers, we have identified three aspects that are common to most of our partnerships. The first one is capability building. So essentially helping the workforce at these companies understand quantum computing, the potential that it has, what we can do today, and what the future could look like for these applications. The second element of that journey is the identification of business use cases, working together with their subject matter experts to identify valuable business problems across the multiple departments that these companies have that we could solve using quantum computing. And then finally, we have building applications in orchestra. So once we have identified those use cases, benchmarking them, scaling them, using the Orchestra platform, which offer a unified way of carrying out this task, with the purpose of taking these applications all the way from R&D to actual deployment. So in this presentation, we wanted to give you an idea of how it's working on these projects between Zapata and these customers, and who better to tell you that than the customers themselves. So I'm going to ask you to join me in listening at a conversation that we recorded with Clena Abuan and Brian Standen, representatives from BP and BASF, where we discuss their journeys in quantum computing and the projects that we have done together in applying quantum computing to chemistry. So let me just project this video. Hi, Clena. Hi, Brian. Welcome to Q2B, and thank you for joining me.
Hi, Jonathan. Glad to be here.
Hi, Jonathan. Thanks for inviting us.
All right. So why don't you start by introducing yourself? Do you want to go ahead, Clena?
Sure. So Clena Abuan, I am part of BP's digital science and engineering team, and I am a principal of digital science. So our team looks at emerging digital technologies that might be 5 to 10 plus years out. And quantum was one of the areas that we focused in as part of our next generation computing theme. So one of the fun things that I've learned about quantum since our journey started back in 2016, trying to understand whether or not this was an area that we needed to pay attention to, is that if you think you really understand something and you've fully understood it, you probably haven't. So that's me. Glad to be here.
Thank you.
My name is Brian Standen. I'm the global head of next generation computing at BASF. And so what that means is that we look at advanced computing technologies and architectures and how they will have impact on BASF. And we investigate those technologies through a series of projects and collaborations as we try to really understand the depth of the technology and how we can apply it then to what we do. So it has that sort of focus that Clena was saying on looking at the future, because some of these technologies are quite new, but we think that there might actually be some opportunity to utilize them even today. And I can't say it better than Clena said it, because every time I think I understand something, I learn something very new in this field, and it completely changes my opinion. But I also think one of the things that has surprised me is how good the community is around quantum, and it's such a friendly and forward-looking community. It's really nice to be a part of that and to embrace it myself. So really unique in that way, I think.
Awesome. So, I mean, both your roles definitely are into innovation, looking at a portfolio of different innovation opportunities that involve new computing technologies, and among them, quantum computing. So, what's your view of quantum among that group of digital innovation initiatives?
So maybe I could start off. So just to say, within our team, we look at emerging technologies in artificial intelligence applications, like I said, next generation computing, which includes quantum, novel robotics, and also advanced remote sensing. So, we look across a broad spectrum of digital technologies, but as far as quantum goes, we really believe that it's going to supercharge a lot of the technologies that we're looking at in different ways. And so it's been really interesting to think about how quantum could impact um, AI applications, especially machine learning, sensing. And so, yes, we think it's going to be there's going to be some really transformative things that come as the technology matures.
Great. What about you, Brian?
So, and this is really thinking within the bounds of next generation computing. I would actually tell you that my first, second, and third priorities end up being quantum, because so much is happening and evolving that we end up looking at that so much more than other technologies. That doesn't mean we don't look at those other technologies. It just means there seems to be much more of a focus that we've developed now, both strategically and organically, on quantum. And I think in many ways, it's in part because of this sort of very natural fit to chemistry, right? The same laws that govern the technology of quantum also are the same laws that govern the development of molecules. And so there's a very clear synergy there for us to be involved in this and to want to advance the field. But for me, I think, it's one of those very rare technologies. And I've done a lot of technology scouting over the past few years, and building off of what Clena said, because I believe this, it is very transformative and one of the few technologies I would reserve for the true idea of a game-changing technology. This could really fundamentally change not just the chemical industry, which is of course of critical importance to us, but I think it actually has a fundamental way of changing how the world works. And that's exciting to me.
Yeah, no, I agree. And, two things that you mentioned that I think are important, right? There are two ways that quantum is enabling this change, right? On some cases, it is supercharging techniques, for example, in the case of machine learning, enhancing the performance of machine learning techniques, but it's also fundamentally changing the way we simulate molecules, right?
Absolutely.
So it has that power of improving other techniques, but also just giving us new ways of solving very, very hard problems that we have been trying to solve for a long time.
Agreed. And if I can add, I think the other element to this to me is that, in saying something like game changing, that can be overselling. And again, for me, this is one of those rare instances where I don't feel like I'm overselling it. That doesn't mean we don't have to manage expectations. And I imagine, Clena, you have the same challenge as I do in managing our expectations on when quantum will be available and the realization of the field as a whole. But I still think when that time comes, then we were not really overselling the potential impact.
Yeah. And I think an important part of that is precisely exploring quantum from a technical perspective through these projects. So maybe going now into your journeys, and specifically the projects that we have worked together on. In both cases, I think the work that we have done with you, with your companies, incorporate those three elements that we believe are fundamental in becoming quantum ready, in a sense. Which is capability building, identifying those business use cases, and then building applications for those business use cases with Orchestra, which is the tool we developed at Zapata. However, I think your journeys started from different points. I think in the case of BP, in particular for the project that we are working on, we started looking at the future, what quantum could do in chemistry, and trying to bring that closer to what we can do today with the devices that we have today. In the case of BASF, I think we started at what we can do today and how we can enhance it with quantum. So maybe just to dig a little bit more into those journeys, I'll start with Clena. Clena, could you share with us a little bit more about the approach that you are taking in quantum and how that applies specifically to the project that we did?
Sure. So like I mentioned, our team looks at emerging technologies that are quite far out still. And the reason for that is because what we're specifically charged with doing is looking at how these disruptive technologies, right, could transform the way that we do business and also accelerate our goals of becoming a net zero company by 2050 or sooner. So with that longer view in mind, although we don't believe that quantum is going to completely replace classical, we thought that it was really important to start thinking about how we can leverage this type of technology. In our early research, we acknowledged the fact that it requires a mind shift, and also that it's highly unlikely that we would be able to just jump in once the technology matures and start to utilize quantum computing. And so we looked at a number of different problems in areas that we believed might have applications where quantum could provide an advantage, and also they were high value to BP. And within chemistry, we started working with BP. We started working with Zapata, and of course BP, because we are BP, to look at a number of different problems that are fundamental to what we do, and also that could be transformative for chemistry. So our goals were really to benchmark classical, to conduct resource estimation, and also to look at what the performance might be on different types of quantum hardware, if possible. And we analyzed quantum resources and what would be needed to solve our problem with VQE. This resource estimation was really important for us to understand, if the algorithm could bring an advantage for our use case, and also what is the estimated time frame that we might be able to see this being used commercially. It also really allowed us to understand where the algorithm could use some improvement, and we did run into some challenges, right. Jonathan, as you know. So, especially in the area of initializing the problem, the number of measurements. And so instead of thinking to ourselves, okay, we just need to wait now for the hardware to mature, we did start to dig into, are there other ways that we could push the technology that we've got today in this NISQ area closer. And so again, working with Zapata, what we did was look at, is there any ways to address this? And so, Zapata also brought some of your proprietary techniques to improve VQE, like robust amplitude estimation. And this was really eye-opening. We were able to demonstrate it on 1 to 2 qubit systems, and we also did demonstrations of VQE on up to 10 qubits, and testing the different techniques that have been developed. We were able to reduce the number of measurements. So this has shown us at BP that there are viable ways to accelerate our path towards chemistry simulation, and also as the devices themselves also improve and mature, the approach is scalable. So it's really been very promising for us, and we're very excited to continue on this journey.
Yeah, and I think in the particular case of the technique that you mentioned, right? I think the project definitely demonstrated how important it is to have this feedback coming from the companies like BP on what are the actual problems, right? And how and measuring how the algorithms can actually perform for a real instance really inform us what we need to improve in the algorithms. I think this is very crucial, and in particular with robust amplitude estimation, we were able to show that we could improve VQE, accelerate VQE, maybe at the cost of having to use a deeper circuit, but still with an approach that would be cheaper than approaches like phase estimation that require fully tolerant quantum computers. So, and in that sense, I think we are effectively achieving that goal of bringing the future a little bit closer to what we can do with the machines today.
I really do want to emphasize, that the going through this process has really allowed us to learn and understand, but like you said, also Jonathan, start to tackle some of the things that we would have run into in trying to leverage some of the technology that we've got today. So yes, it's been really important for us to go through this project.
Definitely. All right. Well, Brian, in your case, can you share with us a little bit about the broader vision that you have for quantum opportunities at BASF?
Yeah, sure. I think we tend to look at quantum as having an impact enterprise-wide. It's not just in the chemistry or in an R&D where we will see the impact, which I think for sure we see that natural fit as I described, but we'll also see this impact in other business. We'll see it in finance. I think we would see it also in supply chain and logistics. All these sort of standard use cases that you hear talking about or are motivating quantum projects, I think will have an impact to us in some way. We might not always lead in each one of those cases. I think that makes sense. We're a chemical company. We would lead more toward chemistry, but we recognize that those will have some sort of impact. And so in the umbrella of next generation computing, we think enterprise-wide. And in fact, we actually looked across the entire enterprise of BASF, which is quite complex, and found a number of use cases that we think could actually fit. But we are also interested in, as Clena nicely put, we're interested in what's happening today, right? What can we leverage today that can get us to full fault-tolerant, error-corrected qubits, and what's that future going to look like? So it's sort of a parallel way of approaching it, where we try to embrace both the future that we see that can happen, but also leveraging what we see today and how we can take advantage of that to really determine where quantum advantage lies within our use cases.
Yeah, which is precisely the focus of this project, right? We look at what we could do today to enhance machine learning. Maybe you can also tell us a little bit more about that.
Yeah, sure. So we really wanted to start with something going with this sort of broad perspective of where we think we can impact the enterprise. We wanted to start with something, a technology that we think could actually have that impact. And for that, it was, for us, it was machine learning. We did focus in this project on, or we are focusing, I should say, on chem informatics, where we really want to figure out how we can predict molecular properties through a number of techniques. But we wanted to start with fundamental work, right, in the near term to assess potential impact. And for us, that involves benchmarking different algorithms against classical approaches. Where can quantum computing actually show us advantage today, if there is any? Or are we doing it okay with classical? And that's, I think, a reasonable conclusion. But the idea is that we want to really try and solve some sort of realistic problem, or at least understand what a realistic problem can look like or needs to be solved in the future. And so I don't think it's that unlike what BP is really trying to achieve. But in our collaboration, we're really starting with today, heading toward the future, as opposed to sort of looking back, if you will, and trying to get that advantage. And we really see this as being how can we leverage quantum as a coprocessor to digital techniques, right? Can we boost classical subroutines where we're looking at it as something that almost sits side by side with our classical infrastructure, or are there other technologies that we would put together to achieve that as well? And so for us, within the collaboration, we're really looking at feature selection and classification as a subroutine of a supervised learning algorithm that would predict specific molecular properties, which of course has great impact for us. And like I said, benchmark that against classical approaches.
Yeah. Yeah. And I think, in that last part, when you were describing like all these approaches that we need to benchmark, right? Like, it's very clear that with quantum computing now, or in other words, quantum computing enables new approaches, in particular for solving these optimization problems. And all of those approaches are heuristics. So inevitably, you need to benchmark them, right? There's no other way you can figure if, this algorithm or this solver is better than this other solver. So benchmarking definitely plays an important role there. And I think in order to do that benchmarking, you need the tools to do the benchmarking, which is where we think as Zapata, we can enter in the game and enable you to do that benchmarking through the tools.
Yeah, I absolutely think that's true. Look, there are a number of technologies that are available to us today. There's quantum-inspired technologies. There are near-term NISQ algorithm and hardware that we can run against. And for the problems that we encounter, right, we really say to ourselves, why wouldn't I take every tool available to me today and throw it against that problem and see if I can actually find some sort of realistic solution. I don't think it's bad if we ultimately come back saying that we don't. That's part of the whole research of this. But it's important that we try. And I think that not only helps to move the field forward, but helps us to understand the fit into our overall technology footprint and where digitalization makes impact. When we think about the journey to quantum readiness, it's to me a very steep curve. And so starting today and building that knowledge base helps us to ultimately be very good at what we do over time. The other thing too is that, as you mentioned, with these optimization problems, it's depending on the scale of the problem. It could be that you find something that's only got an improvement of 1% or 2% against whatever objective you're trying to improve. That 1% or 2% could be a gigantic result for us, depending on the type of problem. And so why wouldn't I want to try and solve something like that? And if I can have it today, again, why wouldn't I? So I think there's a balance to me if we think of this as a portfolio across what's near term, what's midterm, and what's long term, and how can we get to all that, and how does all of that inform each other ultimately?
Yeah. And I think an important part is also how you do this continuously, right? You need to be continuously testing, continuously trying, incorporating the new approaches. So building that capability to do that is definitely important. I'm curious to know about your perspective on these two projects. What do you think the next steps are?
So I think for BP, we've been doing benchmarking work, and I think we're really interested in looking at what early fault-tolerant quantum computers might also be able to bring to the table, both in the chemistry work that we've been doing and also starting to look across the field. So as you mentioned, Brian, actually starting to also really build out that near-term, mid-term, and long-term view is really important for us as well in the different areas that we're interested in. And so I think, our next step is to really start accelerating how we screen through the different use cases that we have, and kind of prioritizing them based on some of the different metrics actually that you mentioned. So yes, we're really excited to start getting our hands even dirtier into this. Yeah.
What about you, Brian?
Yeah, I like this. What you just said, Clena. I think getting our hands dirty is what this is all about right now. Is can we get our hands on the tech? Can we try it and see it succeed, see it fail, or someplace in between where it's even more confusing and you can't actually understand what just happened. But for us, I think in thinking about the project in specific, our collaboration is that I think we want to continue sort of the work we've already done in the first phase of the project, which we're already doing, where we can continue this benchmarking of quantum classical, but to look at it across hardware platforms, which is a whole additional layer of complexity as we sort of think about how these things work. And that I think is fascinating to me, what we're starting to build out. So, again, I think we're trying to investigate something a little more fundamental, and learning how that will work. And we see it as very applicable across so many places and how we can leverage ML, as I've said. So just looking at how we can potentially accelerate that is great. And to what Clena was saying about the validity of our use cases and how well defined they are, and if they're a fit to things like technologies like quantum, rather. It's an iterative process, right? So as we present a use case, and Jonathan, because we've done this with a number of use cases. We start with a use case, we think it's a good one, we got to refine it. We keep doing that until we really see that there is a part of it that could potentially fit, or we conclude that it might not fit. So that's just an ongoing process for us. Excuse me. And I think it's an important part of how you view your use cases over time.
Definitely. And one thing that Clena mentioned, you want to get your hands dirty, right? You want to start playing by yourself, I think. And one thing that we want to do at Zapata definitely is to, help you build that capability to build those applications by your own eventually, and also maintain those applications. I guess this is now leading to what you would like to do in terms of your approach to quantum in general, in particular in your teams. What are the things that you expect to demonstrate to your organizations and the capabilities that you expect to develop in your quantum teams?
So I think for BP, really building on the work that we've been doing in quantum, we're looking to stand up a small quantum center of excellence, or COE. And the purpose of that is really to eventually someday be the place within BP where if you need quantum expertise, we would have a number of quantum computing scientists that would be able to help with different solutions. I don't think that we would say that we're looking to become a quantum software company ourselves, but it's the same with classical today. Actually, we have some computational scientists that help us with particular solutions that BP wants to work on in-house, and then we also have a partner ecosystem that we work with for other software solutions, and I think it would be the same thing with quantum. And so, that's the focus of the quantum COE. But at the moment, that means being able to build that capability and flex that muscle a little bit. So, we're starting to build out with a small COE, and Zapata and others would be a part of helping us with that capability. So really looking at how we could, just like we were talking about, define the use cases that we might see where you might gain some quantum advantage in the near term, the midterm, and the long term. And so we would be working with Zapata to look at a number of different use cases and understand, where these things fit. Are there areas where we might want to do deeper dives, and at the same time, using these types of interactions to build up our own knowledge and also our own capability to be able to do this kind of use case screening in the future ourselves. So really focusing on becoming more self-sufficient and leveraging platforms like Orchestra to be able to screen the different potential.
Yeah, we definitely want to help you build those capabilities. And to a certain extent, getting us out of the job to a certain extent eventually. All right, awesome. What about you, Brian?
So it's hard to follow Clena after that because it was such a nice complete vision, and I agree with everything you just said, Clena. I think one of the things that has evolved for us in our journey, right, is while I said we're sort of trying things out and seeing what the technology does, and we continue to do that today, I think it's less organic than perhaps it was when we first started, where we would sort of say, here's an interesting problem that we can try to use to motivate our understanding of the technology. Rather, we really move with intent to try and solve real business problems at this point. That doesn't mean we're going to solve them. It doesn't mean that we're going to find the solution, but the intent is that we take real problems that we have and that we try to use the technologies available or technologies as we see them in the future to solve these types of challenges that we have. And so we really are focused a lot on performance and the ability to scale what's really viable and what's realistic and what's not. And I see this as very central to my role in understanding how QC will impact our company as it develops. And again, as Clena and I have both said, I think having that sort of understanding of near, mid, and long is really helping with that. We're also building our team. The capability building that Clena was talking about, we're engaged with too. We of course want to leverage the partner ecosystem. We think that it's important to do so, working with you, Jonathan, and Zapata and others as well. It's important that the field advances through those partnerships and that we can bring the use cases to help keep that going. But we do need people internally to understand what quantum is and how it can impact them, so we can have a little bit more germane conversations to the types of use cases we know are out there and that we've already discovered to date. So we're really thinking a lot about how we upskill internally, how we bring people to the table without having to have a deep understanding of the technology, but enough understanding to see how it could influence the work that they do. And being that we're a big and complex company, that is certainly a big challenge for us. And as we're building out our team, we need those people who do have that depth of understanding and who can help to guide others in our organization along that journey. And so we are actually hiring to build our team out at the moment. And I have 3 open positions, just to make a little point out there if you're looking. So I think those are important, right? We want to build up enough capabilities so that we can leverage the good work that we see being done in the ecosystem.
Definitely. Unfortunately, we are coming to an end for the session, but just very quickly, I had a final question. So imagine that you have a quantum genie, right, that can grant you a quantum wish with high probability of success. What would you ask the quantum genie for? Brian?
I would say, oh, great genie, can you please give me fault-tolerant error-corrected qubits tomorrow, along with the algorithms to exploit that computational power, and primarily not only so we can use it, but so that people will stop asking me when we'll see it.
That's a great one, Brian. Yes, I can completely understand that one. And I think, I would add to that and say, maybe the wish that I would have is to have the power to intuit the problems that quantum computers can solve that we're not thinking about. So I think, especially, for us, we're thinking a lot about problems that we have today with the way that we do things today, but it's really hard to shift your mind to things that maybe we've stopped exploring because they just seemed impossible before. Yeah. So and then maybe in order to build that the capability that goes with it, just if we could broaden the pipeline, because I think that's happening. I'm excited to see that, but just seeing more people get into the quantum computing field, different types of minds looking at these types of problems. So that would be my wish.
That's great.
Totally.
Yeah.
Awesome. Well, thank you very much. Thanks a lot for all of those insights, and thank you to our audience for the attention.
Thanks for having us.
Yep. Thank you.
Take care. Bye-bye.